So, hi and welcome back to today's videos. Today we're going to see a small example of an integration over a vector field along a curve. So, let's say we have a vector field V that is defined on R3. So it also maps to R3. And it's defined as v of x1, x2, x3 equals x1, x2 squared, x1, x3, and x3. And let's say we have a curve, gamma, that maps the interval 0, 1 to R3. And that is defined as gamma of t equals t squared, t to the third. So remember, what we want is we want to evaluate the integral of v along the curve gamma. And that is the same thing as integrating over the time interval for gamma. So here that is 0, 1. And we integrate over the function given by the scalar product of v of gamma of t and gamma dot of t dt. That is the definition of a line integral over a vector field along a curve. So to evaluate that, we first need to evaluate the expression v of gamma, and then we need to evaluate gamma dot, and then we can compute the scalar product, and finally the integral. So let's start with v of gamma of t. That is, by definition, the same thing as v of, well, gamma of t is t squared, t to the third. And then we use this definition here of v. So the first coordinate of the resulting vector is first coordinate of the input times second coordinate of the input squared. So the first coordinate of the input is t. The second coordinate is t squared. And that means we have t times t squared squared. For the second coordinate, x1, x3, that means we have to multiply the first coordinate of the input with the third coordinate of the input. So we get t times t to the third. And finally, we just get x3, the third input coordinate, which is this one here. So here we get t to the third. And let's simplify that a little. So the first coordinate is t times t to the power of 4. So that's t to the power of 5. Then we have t to the power of 4. And finally, t to the power of 3. So that is the vector of that vector field at the point that corresponds to time t on the curve. Second, we will also require gamma dot of t. This here is gamma. So we just differentiate that coordinate-wise. And that means what we get here is 1 for the first coordinate, 2t for the second, and 3t squared for the third. So now we are ready to compute the integral here. And let's do just that. So the integral of gamma of v ds is the integral from 0 to 1 over v of gamma of t, scalar product with gamma dot of t dt. So what we get is, well, that scalar product. That simply means we take v of gamma of t transposed and multiply that with gamma dot. So we have t to the power of 5, t to the power of 4, t to the power of 3. We multiply that, or the transpose of that vector, with 1, 2t, 3t squared. Again, this is the orange part. This is the green part here. And we need to integrate that dt. So what we get here is the integral from 0 to 1 of t to the power of 5 plus 2 t to the power of 5 plus 3 t to the power of 5 dt. So that's altogether 6 times t to the power of 5. So 6 times this integral t to the power of 5 dt. And that is t to the power of 6, right? The integral is t to the power of 6 over 6 times this factor 6. So those factors cancel out, and we just get t to the power of 6 from 0 to 1, which is 1. So the value of that line integral over the vector field v along the curve gamma is simply 1. So that concludes this example. Next, we're going to discuss special properties of gradient fields in the next couple of videos. I'll see you then.